bias variance. Okay. So I will explain what that is. This is just a very preliminary introduction in this class, and later on as we progress we will come back to this at other points. Okay. So let us start off with the assumption that, and in many cases I will be looking at regression because it is easier to write, but you can similar concepts you can also have for classification. Okay. So I am going to assume that your actual data is being generated by a system of this form, right. So there is a function f, right, which is what you are trying to learn about, but the data that is given to you, the y's that are given to you are actually corrupted by some kind of noise. Okay. Right. So if you remember last class, at least the last class I was teaching, we were talking about a joint distribution over y and x, correct. So I said there is some joint distribution over y and x, you do not know what the joint distribution is, you are only given samples drawn from that distribution. Okay. Here we are making a specific assumption about the form of the joint distribution. I am assuming that there is some kind of an underlying deterministic function f, okay, which is operating on my input x, but then it is corrupted by some stochastic noise which we will call epsilon, okay, and that gives me the joint distribution over x and y. Okay. So this process together gives me the joint distribution over x and y, and we are going to assume that expected value of epsilon is 0, variance of epsilon is some sigma squared. Okay. So the expected prediction error at some point x naught, right, is essentially the right. So we knew what the expected prediction error was, right. So that was y minus f of x whole squared, but at the point x naught I am just conditioning on x naught, and this is my prediction error, right. So it turns out that I can rewrite this expectation as a sum of 3 terms. Okay. So what are the 3 terms? The first term that's fine. Okay. So the first term is essentially the error that I am going to see, right, by looking at the estimate that I will get from a specific data instance, okay, from the estimate that I will get as an expectation over the entire training, the sample from which the training data is being drawn. Okay. So if I build the classifier multiple times, if I build the classifier f hat multiple times, okay, so this is the expected output that I am going to get for f naught, x naught, right, and this is the output I am getting for this specific instance of data that I have. Okay. So that is one component of the error. Okay. The other component is, okay, look at the expected prediction I will make for x naught, okay, taken over multiple training instances, what is the expected prediction I will make for x naught, and what is the expected output I am going to get, true output I am going to get, right. What is the expected true output I will get? It's expectation of y, and what will be the expectation of y? In this case is f of x naught, and then there is a underlying error sigma squared that just comes from the fact that I have a variance of sigma squared in my, if I am going to make any single prediction, okay, even if I am going to give you the output as f of x, okay, even if my output is f of x, there will be an expected error of sigma squared because my y has that noise in it. Okay. Does it make sense? So this term is typically called the okay. So this term is typically called the variance of the estimator f hat. Okay. This term is called the bias. This term is called the bias of the estimator f hat. So one way to think about it is the following, right. So f is my true function, right. So regardless of how much ever data I am getting, whatever data I get, right, regardless of whatever data I get, right, I expect to make at least this much error from the true function f. Okay, so that is the bias, okay, and the variance is essentially given a specific instance of the training data, okay. So what is the expected error I am going to make, right. So this is the bias, this is the variance, and that, what about that part? That is hopeless, okay. I mean regardless of how powerful your classifier is, you can't get rid of that sigma squared because that is the inherent noise in the data, okay. So that is nothing you can do about it, okay. So now by choosing your classifier appropriately, okay, you can trade off between the bias and the variance, okay. So I will just, for simplicity's sake, I will take the example of our k nearest neighbor classifier. So all of you know about KNNs, right. So it is very easy to talk about bias and variance in KNNs, right. So let us look at this. So what do you think this variance term will be for the KNN case? Essentially I am looking at a prediction I am making over many instances, right, and the specific prediction I make for one training set, right. So what would that be? If you know, if you think about it, the prediction I am making is essentially just the mean of k numbers, right. So what will be the variance of that prediction from many different samples drawn? It will be the base variance divided by the number of samples. Should have seen that in probability theory course, okay. If you have not, okay, I have a later I will be doing a session on statistics, okay, and a little bit on hypothesis testing and so on and so forth. At that point we will go back and look at it, but just this is the basic setup, right. So I have some distribution, right, I take samples from it, okay, I have some distribution P, I draw samples from that distribution P and I try to estimate the mean and variance of that distribution through those samples, okay. So now the variance of the estimates of the mean made from this samples is essentially given by the variance of the underlying distribution divided by the number of samples which you are drawing every time, okay. So this assumes that you have drawn the k samples many times and you have made an estimate of what the mean will be, right, and this is the specific estimate of that mean. This is essentially the variance of that estimate, right. So that is essentially sigma squared by k. And what about this? So this term, right, so this is essentially my expected prediction. This, I mean, there should be an expectation here over the training data, right. Okay. So this is the expected prediction I am going to make, right. So I am going to take all the k nearest neighbors of a data point, right, take the average of that will be the prediction I am making. So this is the prediction that I am going to make, right, and this is the expected value of y that we have plugged in here, which is f of x naught, right. Okay, now let us try and look at this, what happens when I change my k, right. If I increase my k, what will happen to the variance? It will decrease or increase? Decrease. What will happen to the bias? That is an interesting question. If I increase my k, what will happen to the bias? Increase. Why? Sorry?
It's a subtraction.
Louder please.
We are subtracting from.
It is not just the subtractive part, right. So if I increase k, essentially what is going to happen is I am going to start pulling in data points that farther and farther from x naught, right. I will be pulling in data points farther and farther from x naught, therefore my estimate of f of x naught is going to be an average of a lot of dissimilar data points. So the error is going to be higher. So for a fixed dimension, increasing k, right, is going to essentially pull in data points that are more and more dissimilar than the query point, right. The query point was x naught, so I am going to go farther out, and therefore this will essentially become larger, okay. So as k becomes larger, my bias increases in KNN and my variance decreases. Variance decreases just because I am taking an average of more data points, right. There is nothing to tell you that the average is correct, it is just that I am telling you that the average will look the same even if I change the training data, right, because I am averaging so many data points, correct. And this part of course we can't do anything about, that is the irreducible bias. So what does this tell you? So last class we had this discussion about increasing k, what does it do, right. What did we say when k becomes larger? I did not say anything about it becoming more correct or not, I said it will look more stable. Why does it look more stable? Because my variance goes down, right. So when I say that classifier is more stable, estimator is more stable, because the variance has gone down. And also if you look at the classification surface that you will get, right, the separation surface that you will get, it will be a lot smoother if k is very large, right. I told you when k is 1 you are going to get lot of isolated islands of different classes and so on and so forth. When k, for small values of k, you will find that the classification surface is very complex, right. It is not like a linear thing, or you can predict very complex functions also, right. It is easy to think of the complexity in terms of the classification surface, but function wise also you can think of very complex functions if k equal to 1, right. If k is larger and larger, the function has to be smoother and smoother, you cannot have rapid variations in the function, right. That essentially means that when k becomes larger, your function class becomes simpler, right. It kind of looks counterintuitive, right. I am giving you a lot of k, but then your function class typically becomes simpler because it has to have all the smoothness constraints on it, right. And as k is smaller, then your function class can be larger. So your regressor or your classifier is more complex, okay, if k is smaller, and it is less complex if k is larger. And in general that is the case, that if your classifier is more complex, your variance will be higher, your bias will be lower, okay. And if your classifier is less complex, your bias will be higher and your variance will be lower, okay. So this is usually the case, okay. And this also lets us understand why k means does not perform that well in high dimensions. Why is that? Huh?
One small.
Sorry?
One parameter gets changed a lot.
Yeah, no, see, this is even simpler than that, right. So take the bias term, right. So even for low values of k, right. So if you take a very high dimensional data, you can with a little bit of analysis show that the with very high probability the nearest neighbors will be far away from the any query point. You can take any query point, right, and draw a ball around it, the ball is more likely to be empty than filled. Okay. So, for the radius of the ball depends on the dimension, it becomes larger and larger as the p becomes larger. Okay. And so essentially it means that even for small values the bias will be high, even for small k the bias will be high because the expected distance to the nearest point will be larger in a high dimensional space. Okay. So not only will the variance be high because you have small k, even the bias will be high, and obviously increasing k is not helping you in that case. Okay. So this is just a pretty rudimentary discussion on bias and variance at the trade-offs, but I just wanted to give you a feel of that, and you have to keep this in mind later on as we are looking at every classifier that we will see, right. And specifically now we are going to go into linear regression, right. So what about bias and variance in linear regression? Does linear regression have any bias? Must be, right, seems to be a very simple classifier. Okay. We will talk about that later, but the point is, yes, so you will have to, any classifier that you are going to be building or thinking about in the future, right, you will have to start thinking about, okay, what is the bias, what is the variance, okay, is it appropriate to use this classifier in this setting, right, and things like that.